We've seen how to specify an index model by choosing a CDF, and we've also seen how to write down the likelihood, which would allow us to calculate the conditional maximum likelihood estimator. But what do we like to have along with our estimates? Well, standard errors. To find out how to calculate the standard errors for index models, we'll rely upon the large sample results for conditional maximum likelihood estimation from our previous lecture. Recall that for a potentially misspecified conditional likelihood model, the MLE beta hat is consistent for beta naught, the pseudo-true parameter value, and is also asymptotically normal with variance covariance matrix J inverse, K, J inverse, where J is defined as the minus expected value of the Hessian matrix evaluated at the pseudo-true parameter value beta naught, and K is defined as the expected value of the outer product of the score vector evaluated at beta naught as well. In the special case where our model is correctly specified, the asymptotic variance matrix simplifies to J inverse. It turns out that the calculations of J inverse K J inverse are pretty complicated for index models. So if we want to rely upon the robust asymptotic variance matrix estimator, we'll leave that to the computer to calculate for us. However, it's instructive to go through the calculation of J inverse because it introduces a clever trick that can be used more broadly when we want to calculate the asymptotic variance matrix of a correctly specified conditional likelihood estimator. So to be clear about where we're heading, we're going to assume, for the purposes of this derivation, that our index model is correctly specified, and then we'll ask how we can calculate J, which is going to require us to evaluate the Hessian. Of course, the Hessian being the matrix of second derivatives. To calculate it, we should start off by calculating the vector of first derivatives, namely the score vector. Using our result for the log likelihood of an index model from the previous video, we can calculate the score as follows. The derivative of the log likelihood with respect to beta takes the following form. First, we will differentiate yi times the log of g of x prime beta with respect to beta. This gives us yi multiplied by 1 over g of x prime beta, and we're using the chain rule here. Then we have to differentiate g of x prime beta with respect to beta. We've done this already in the lecture when calculating partial effects, so we know that the result there is little g of x prime beta times x. Almost the same exact calculation for the next term, although here we've got to keep track of the minus 1. Now, simplifying the following expression by putting it under a common denominator, we see that the score vector is equal to little g of x prime beta times the vector x multiplied by y minus g of x prime beta over g of x prime beta times 1 minus g of x prime beta. Now we'll use the score to try to calculate the Hessian before giving up because it's a total nightmare. The Hessian is defined as the derivative of the score vector with respect to beta prime, so that we obtain a matrix of derivatives. So let's write the score vector from the preceding slide in the following form. I'm going to split off a yi minus g of x prime beta from the rest of the expression, which is to say the fraction little g of x prime beta times x over big G of x prime beta times 1 minus big G of x prime beta. I'm now going to use the product rule to start differentiating the expression in these parentheses. Right, so the first thing I need to do is differentiate the first factor and multiply it by the second. When I do that, I will obtain minus little g of x prime beta squared times x prime divided by big G of x prime beta times 1 minus big G of x prime beta. I will add to this, again continuing with the product rule calculation, the first factor, yi minus g of x prime beta, multiplied by the derivative of the second factor with respect to beta, and this looks like it's going to be a bit of a pain. I'm pretty sure that I will make some kind of mistake if I try to calculate this derivative, and that's not going to work very well for the video. So instead of calculating this derivative, I'm going to stop short and just give it a name. It's a nasty, awful mess, so let's define it as capital M for mess. It's a function of x and beta. And let's see if we can somehow avoid having to calculate this. So here's where the clever trick comes in. If we wanted to calculate the matrix J directly, we would first need the Hessian, which, as we saw on the previous slide, would require me to work out the exact form of that nasty, awful mess M, and we would then take the unconditional expectation of that Hessian evaluated at beta naught. So here's a different idea. Rather than taking the unconditional expectation, let's see what would happen if we took the conditional expectation given x. Now remember, I didn't actually finish calculating the Hessian. That's okay. Let's just leave that notation from the previous slide alone. Let's just leave that capital M for nasty, awful mess and see if we can get around having to compute it. All right, so using the expression from the previous slide, notice that the first term, somewhat nasty-looking fraction, depends only on x and beta naught. That means that conditional on x, it is a constant. That was easy. Now let's look at the next term. The next term is something simple, yi minus big G of x prime beta, multiplied by something nasty. But when we calculate the conditional expectation of the product of those two terms, given x, notice that the second, capital M, is also a function of x and beta naught only. That means that it is a constant with respect to that conditional expectation and can be pulled out. All right, well, does that really help us? Don't we still need to calculate M? Well, here's the real trick. If we assume that the model is correctly specified, namely, if we assume that indeed g of x prime beta naught is the probability that y equals 1 given x, then that is the same thing as assuming, because recall that for a binary outcome model, the probability that y equals 1 given x is the conditional mean of y given x. That assumption of correct specification is the same thing as saying that this expression is 0. Why? Let's just write it out. By the linearity of conditional expectation, we can split this up into two pieces. The first piece is the expectation of y given x, and the second is, well, it's the expectation of g of x prime beta given x, but that's just a constant with respect to x. So we have expectation of y given x minus g of x prime beta naught, but if the model is correctly specified, then that is precisely the conditional mean of y given x, and this term equals 0. So we see that we were able to avoid calculating that nasty expression m, and the way that we did it was by taking conditional expectations and very fortuitously arriving at a term that is a kind of a residual, and the expected value of such a residual, conditional on x, is going to be 0. So now we are ready to calculate j. We will do this using iterated expectations in the following way. J is defined as negative expectation of the Hessian evaluated at beta naught. By iterated expectations, that's the same thing as negative of the expectation of the Hessian conditional on x. And we've just calculated that inner expectation. It's the following. It's not the prettiest expression in sight, but it's not too bad. And notice that we arrived at this expression by relying upon correct specification. So this way of calculating j would not work if we hadn't made the assumption that the model was correct, but because we did, it gave us something very straightforward. The calculation from the following few slides gives us the following asymptotic distribution for correctly specified index models. where all that I've done is I have substituted the specific value for J inverse in an index model under the assumption of correct specification into the general result for conditional maximum likelihood that I showed you earlier. It turns out that the following expression provides a consistent estimator of J inverse. And again, just to caution you that this calculation assumed correct specification. We may not want to do this in practice. If so, we can always fall back on the robust asymptotic variance-covariance matrix. It's a pain to calculate by hand, so I won't attempt it, but R can do it for us.